Now we're going to talk about derivatives involving vectors. Let's start with an ordinary derivative of an ordinary function f of x. The derivative at x gives you the slope of the tangent line at x. Another way of thinking about this is if we change x by a little bit, dx, then the change in the function, df, is very well approximated by df dx, the derivative, times dx. This is precise only in a limiting sense as dx goes to 0, but we can really get away with just thinking of these as small quantities. Now, if our function f depends on 3 variables, x, y, and z, it's still a scalar, but now it's a function of 3-dimensional space, we can still ask the question, if we move around by a little bit, dx, dy, and dz, how does the function f change? Now the formula is given by the chain rule. df is equal to df dx times dx plus df dy times dy plus df dz times dz. That tells you that if we change x, y, and z by little amounts dx, dy, and dz, how much df changes. Now, it's a bit of a mess notationally, but we can clean it up by thinking about vectors. Let's first introduce a vector that represents how we've changed our point x, y, and z. Let's group together dx, dy, and dz into the x, y, and z components of a vector dr. This is the displacement vector. And now we want to dot this displacement vector into another vector in order to get df. Well, that other vector is going to have components df dx, df dy, and df dz. And we're going to call that vector the gradient of x. So now we can answer the question, how does f change when we move around a little bit, with a much more compact equation that says df is the gradient of f dotted into the vector displacement. Now in the one-dimensional case, we would have somehow divided by dr to think about this as a slope, df dr. But we can't divide by a vector. So what are we supposed to do here? Well, let's think about the dot product in terms of the magnitude and the directions. Remember, the dot product is equal to the product of the magnitudes times the cosine of the angle between them. So let's write df as the magnitude of the gradient of f times the magnitude of the displacement dr times cosine of theta. So think of theta as a little angle that kind of sweeps around and tells you whether you're moving around in a direction dr that's either parallel to the gradient of f when theta equals 0, or perpendicular to the gradient of f when theta equals 90 degrees. Now, when theta equals 0, we're parallel to the gradient of f, and cosine theta is at its largest. It's equal to just 1. So this is telling us that the direction of the gradient of f is the direction in which f changes the most. And the magnitude of the gradient of f is just equal to the rate of change, because now this is a scalar equation with theta equals 0, so we can just divide by the magnitude of dr and think of it as df over dr, which is the slope. So the gradient points in the direction of greatest increase of f, and its magnitude is given by the rate of change in that direction. Now, let's think about what happens when theta equals 90 degrees. So we're moving in a direction orthogonal to the gradient. Well, now the cosine of theta is 0, and the change in f is 0. This means that this special direction orthogonal to the gradient is a direction in which f doesn't change at all. This is called a level set of f. If you have any function, and you think about the subset of 3-dimensional space over which that function doesn't change, that's called a level set. So this means that the gradient is actually perpendicular to the level sets, because when you're 90 degrees away from the way the gradient points, you move in a direction in which f doesn't change. Finally, let's think about what happens when the gradient vanishes. Now, no matter what theta you choose, no matter what direction you move in, the change in f is 0. This is a stationary point of f, a maximum, a minimum, or a saddle point more generally. These are the 3 key properties of the gradient. The gradient of a function f points in the direction of greatest change of f, and its magnitude is equal to the rate of change in that direction. The gradient is orthogonal to the level sets of the function f. And finally, the gradient vanishes at extrema, i.e. maxima, minima, and saddle points. These properties are all very nicely illustrated in terms of a two-dimensional example. So let's now think of a scalar function of just two variables, x and y. And we'll think about it as the height of a hill, h of x and y. If you're a hiker, you have some experience with contour maps. This is a map that shows you the elevation in a two-dimensional setting. You just take the level sets of your function h, i.e. the curves in the xy plane where the altitude is constant, h of xy is constant, and each of those curves is a contour line, and you just draw those contour lines. So a contour map is nothing but the level sets of a function. Now, let's think about what the gradient is doing for this hill. If you're far away from the hill, the slope is very small, the ground is quite flat, and so the gradient vector is quite small, and you can't even see it yet. But if you walk to a steep part of the hill, now the gradient vector is pretty big. Its magnitude is the rate of change in the direction of maximum increase. So you can see here that it's pointing straight uphill and it's fairly big. Now, when you get to the top of the hill, you're high up, but the gradient is again small because it's flat up there. It's a point of maximum of the function, and so the gradient is actually vanishing. And if you walk down the other side of the hill, now the gradient points not in the direction you're going, you're walking downhill, but it still points uphill. It's telling you the direction of greatest increase. This particular hill has another maximum, the smaller hill over here, and it has another place where the gradient vanishes in the pass between the two peaks. Okay, so now I'm going to play this animation, and you should watch and make sure you understand all of the properties of the gradient vector as our little person goes on a walk. Now back to three dimensions. In a three-dimensional function, the interpretation is the same, but you have to think about your displacement in three dimensions. So, for example, if our function t of x, y, and z is the temperature in the room, the gradient of t at each point points in the direction where the temperature increases the fastest. So, if you're cold, follow the gradient vector and you'll quickly end up at a very warm place. Let's do an example. Let's consider the scalar field given by f of x, y, z equals x squared plus y squared plus z squared. This scalar field just gives you the distance squared from the origin. Computing the gradient, we find that it is given by 2x, x hat, plus 2y, y hat, plus 2z, z hat. But this is actually equal to twice the position vector r, where r is x, x hat, plus y, y hat, plus z, z hat. R, the position vector, just points to where you are in three-dimensional space. So the gradient of this function f was 2r. Let's see if this makes sense in terms of the properties of the gradient that we've been discussing. First, the gradient points in the direction of maximal change, and its magnitude is the rate of change in that direction. Well, this gradient points radially. That makes perfect sense because this function is just the distance squared from the origin. If you want to increase that as fast as possible, you should aim straight away from the origin. So the gradient does point in the direction of greatest increase. And the magnitude of the gradient is just 2. That makes sense because this is the distance squared and the derivative of r squared is 2r. Property 2 of the gradient is that it is perpendicular to the level sets of the function. This function is distance squared, so the sets on which it is constant are the sets of constant distance from the origin. i.e. spheres. Well, is the gradient perpendicular to the spheres as it's supposed to be? Yes, because the position vector points radially outward. And finally, the gradient vanishes at maximum, minima, and saddle points. Is this happening here? Well, this function just has one minimum at the origin where it's equal to 0, and indeed, the gradient vanishes at the origin where r equals 0. There are two other derivatives besides the gradient that arise in vector calculus. These are called the divergence and the curl. A full understanding of divergence and curl actually has to wait until after we've covered integrals and the fundamental theorem of calculus, but for now we'll just introduce the formulas and get used to them. We can guess the formulas by taking seriously this little del thing we've been writing for the gradient of a scalar. Let's think of del as a differential operator given by d by dx x hat plus d by dy y hat plus d by dz z hat. Now the gradient of f can be thought of as del acting on the scalar f. But there are other things we can do with vectors besides multiply them by scalars. We can dot them with vectors and cross them with vectors. So let's try doing that with our vector-valued operator del. If we dot del with some vector field v, then we get dvx dx plus dvy dy plus dvz dz. We get an operator that takes a vector field v and returns a scalar field, which we call the divergence of v. And if we instead use the cross product, we get a more complicated operator, which we call the curl of v, which takes a vector field v and returns a scalar field, the curl of v. These derivatives talk to each other in some interesting ways. For example, suppose we started with a scalar field f, we computed the gradient of f, and then we took that vector field and computed its curl. So we had the curl of a gradient of f. If you write out all the terms, you will find that this is actually 0, no matter what f is. The curl of a gradient is always 0. Now the really interesting thing about this is it actually goes the other way. I'm not going to prove it, but there's a theorem, it's a special case of the so-called Poincaré lemma, that if you have a vector field whose curl is 0, if the curl of v is 0, you can always find a scalar field f such that v is the gradient of f. F won't actually be unique. You could add a constant to it, and it would still be a valid scalar field f whose gradient is equal to v. But nevertheless, you can always find such a scalar field if the curl of your vector field vanishes. This is very important in electrostatics. For example, the curl of the electric field is 0. That's why you can introduce the electric potential phi, which is given by E equals minus grad phi with the conventional minus sign. A very similar property holds for divergence and curl. If we take a vector field W, we compute its curl of W, and then we compute its divergence, we will again find that all the terms cancel. The divergence of a curl is always 0, no matter what your vector field W is that you start with. And again, there's a theorem that says it goes in the other direction. It says that if you have a vector field V whose divergence is 0, you can always find another vector field W such that V is the curl of W. And this will be used in advanced electromagnetism to introduce a vector potential, which is analogous to the scalar potential phi of electrostatics. It's traditional when introducing divergence and curl to give some kind of interpretation along the following lines. If we visualize our vector field as a bunch of little arrows, and we think about them as representing the flow of a fluid, then the divergence at a point tells you how much the fluid is kind of spreading out at that point, and the curl at that point tells you sort of how much the fluid is rotating around. Now this is true, but it's not very precise, and it can actually be misleading because there are plenty of vector fields where it looks like the fluid is spreading out, but the divergence is actually 0. And similarly, it can look like the fluid is rotating around, but the curl is actually 0. So I include this interpretation mainly as a word of caution that you're going to see this, but you can't take it to the bank. If you want to really understand what the divergence and curl mean, you actually need integral calculus. And for that reason, the next topic in the video series is going to be vector integrals.